Beautiful geometric shapes are hard for me to ignore. For a while, I would find obscure curves on this website and try to recreate them in a graphing calculator. Why I have this slight obsession, I'm not sure, but it was no surprise to me that when this video was shown to me one day, I wasn't able to stop thinking about it. So I recreated it in Desmos immediately, which was simple enough. There's a circle centered at the origin, and along its edge we generate more circles. Another way we can put this is that each of these circles' centers is a fixed distance from the origin. Each of these has a radius equal to its center's y component. This means that all the circles rest perfectly upon the x-axis. And let's just take a moment to enjoy the simple beauty in this. With such simple rules, an elegant result has emerged. Now I was presented with another challenge, to define the edge of the shape created by these circles. At first, because of its connections with circular geometry, I thought to define this with a polar function. My first choice was a sine function scaled by the circle's radius, which was also added to it. I tried varying the exponents on the sine to 1/2, and for a while I thought I had it with an exponent of 2/3. Upon closer investigation, this actually wasn't correct, and this was really hard for me to accept at first, because this answer seemed so elegant and simple, just like the rules that created it. But I realized that even if this was correct, it wasn't satisfying. The exponent of 2/3 really means nothing to me if I found it by chance. So I decided to reevaluate the problem. By defining the edge parametrically, that is to say with x and y being their own functions of a time variable, t, I thought I would likely have more success in meaningfully and intentionally seeking the answer. To do this, I broke the end result up into two parts. First, we have to get from the origin to the center of a generated circle. Then we have to get from the center to the point where its edge is along the shape's edge. For each circle, there's only one point shared between its edge and the edge of the shape. So the first part is relatively simple. With t as our time variable, functioning as an angle, x and y are cosine and sine respectively, and scaled based on the radius of the main circle. The second part we'll have to think about. It's clear that the generated circle's edge share one point only with the shape's edge, but how do we define that? Let's first reframe the question. Let's imagine that a circle is traveling along the edge of the larger one and scaling appropriately according to the rules that we defined at the beginning. Now, if we have to trace the shape with a pencil attached to the generated circle's edge, what will its angle be relative to the circle's center? Let's call this our pointing angle and analyze a couple of extremes. When t equals 0, the pointing angle is negative pi over 2, or negative 90 degrees. When t equals 90 degrees, then we can see that the pointing angle is the same, 90 degrees. Now this looks like a linear relationship, so let's check the in-between point. And it looks like it's a linear relationship because when t equals 45 degrees, the pointing angle seems to be 0. So let's make a relationship. The pointing angle is negative pi over 2 plus 2 times t. And now that we have that relationship, we can do the second part. The x and y components can again be cosine and sine functions with this function of t as an input. The scale in this case isn't based on a fixed radius as with the first part, but rather the variable radius of the generated circles. This radius is defined as the y component of the circle at angle t, so it's the radius multiplied by sine of t. We now have a set of parametric functions with an angle t as an input and x and y as an outputs. So let's graph them and see how we did. And it appears to be accurate. Not only that, but it makes sense. For a while, I was stuck at this odd, elegant solution with no sense of meaning, but now I have a deeper understanding and appreciation for this shape. I believe mathematics is both a science and an art. As a science, it requires strict adherence to its rules. But as an art, it rewards you when you do so. Because, when it's taught and learned correctly, math is a beautiful thing.